Before we begin, I'd like to tell you why you should care about Bayes' theorem. Well, Bayes' theorem is a mathematical framework that helps you understand how we think. It helps you understand how we change our beliefs when information comes in. It helps Netflix recommends what you should watch next. It helps cars drive themselves. It helps doctors analyze patients, and so much more. I hope you enjoy this video. Let's try to imagine something. So there is a person called as, let's say, uh, Alan. Alan is a person. Now, say we know a few things about Alan. Alan lives a quiet life. Alan lives a quiet life. He is very tidy and organized. If you know this about Alan, Alan likes to lead a quiet life, and also that he is very tidy and he is very organized. Now, if I were to ask you, which one do you think Alan is? Is A, Alan is a street hawker? B, Alan is a mathematician? As a mathematician. Now, given these two things, which one are you more likely to believe? I bet that many of you think that Alan is a mathematician, not street hawker. Alan is a mathematician. Now, for some reason, people like to believe that because they hear, okay, he leads a quiet life, he's tidy and organized. That seems like a person in academia. Maybe he's a mathematician, maybe in a college something. But what happens is we tend to overlook a very key and important fact, and that is simply that there are many street hawkers in India, many street hawkers in India, and there are very few mathematicians, very few mathematicians. Now, I obviously in my life encounter way more mathematicians than I do street hawkers. That is basically because where I work, and if you think about it, there might be maybe 200 street hawkers for every mathematician out there in India. So the odds of a person being a street hawker is way higher than him or her being a mathematician. So why is this? Why do we think like this? What makes us think that a person is more likely to be a mathematician than a street hawker when the evidence is clearly against that? That is what Bayes' theorem tries to accomplish, to deviate us out of, like take us out of this logical fallacy and put us in rationality. Okay, so let us try and visualize it. Before we look at any formulas, let's try and visualize the whole thing, right? So now what Bayes' theorem wants to find out and helps you to find out is what are the odds that someone is a mathematician given the evidence that he or she leads a quiet life and is tidy and organized. So we have a hypothesis that the person is a mathematician. We have a hypothesis that the person is a mathematician. Let me use a different color. Hypothesis that the person is a mathematician, and we have evidence that the person leads a quiet life, and is tidy and organized. Tidy and organized. Now, how do we visualize this in terms of probability? So we do that by writing it something like P of H given E. H is just the hypothesis and E is just the evidence. P of H given E. So that is the probability of hypothesis given evidence. So in simpler words, what are the odds that the person is a mathematician given these data? So when we learn, so suppose we want to find out some person is a mathematician and we get some evidence, what are the odds that the person is a mathematician given what we have just learned about them? That is the heart of Bayes' theorem. This is what Bayes' theorem wants you to be able to find out. Let's take that from the top. Now, something I forgot to mention, this little line can be read as the given. Okay. So P of H given E. Okay. So what are we trying to find out? We want to find out how many mathematicians, what is the chance that a person is a mathematician when we know that he or she leads a quiet life and is tidy and organized. And let's see, if we imagine that these many street hawkers are tidy and organized and also lead a quiet life, and these many mathematicians do the same. Okay, so what we want to find out is what are the chances of a person being a mathematician when we know that that person is tidy and organized and leads a quiet life. So this is what we want to find out. This is what P of H given E wants to find out. This is how you internalize it. This is how you visualize it. Okay. Now, on to the formula. So, in conditional probability, you might have seen P of H over E equals P of H intersection E. This I like to read this as P of H and E. P of H and E. That this means that both H happens, event H happens, and event E happens. Both of them happen over P of E. At the same time, you must see this P of E given H. P of E given H. The person is leading a quiet life and is tidy and organized, given that that person is a mathematician. This is what we want to find out, and that can be written as P of E intersection H, or P of E given P of E and H, sorry, over P of H. Now, a funny thing here, P of H and P of E and H, aren't they the same thing? Because event E happening, event H happening, doesn't matter which way they happen, but both of them are happening. So they are both essentially the same thing. So let us rewrite that as K over P of E in this case, and this case P of H. Now, P of H given E, that can be rewritten as these terms. Now, what are we going to do here is we're just going to define K in terms of this and this. So K just becomes P of E given H multiplied itself with P of H. So if we implement this value of K into this equation, we get P of H given E equals P of E given H multiplied with P of H over P of E. Okay, if is the formula of Bayes' theorem. This is the infamous formula of Bayes' theorem, and this is what we want to find out. Okay, and this thing is the same as what we visualized right here. Okay, but in computation, when you go to compute it, P of E is always something else. So let us visualize that too right now. We are going to look at what P of E expands into. So let me tell you that real quickly. So P of E expands into P of E given H, multiply that with P of P of H plus P of E given H complement. That's just H complement is everything in the universe except for H, and P of H complement. Now, if we expand this in just conditional probability terms, that would give us P of E intersection H over P of H, and P of H, add that with P of E intersection H complement or P of H complement, multiply that with P of H complement. We can just cancel these out, and here we are left with P of E intersection H, P of E intersection H complement. Now, if we visualize this in terms of a Venn diagram where this is E and this is H. So E intersection H would be this little part right here, and P of E intersection H complement. H complement is everything in the universe but H. Okay, so it's all of these stuff, everything here, everything in the universe but H complement, and P of E, and which is just this little part right here. So as you can see that this part is what we are essentially concerned with. So when you look at these two things closely, you realize that this is just P of E. So like this part coming from this part of the addition, and this little sliver coming from this part. This whole thing is just P of E. Okay, and a little bit jargon at this point. This part is called as the posterior probability. That means what are the chances of H being true given that E is the evidence, H is the hypothesis. This part is known as the likelihood of the evidence being true if the hypothesis stands. This is just P of H is called as also the prior probability, and P of E is known as the marginal likelihood. Okay, marginal likelihood. Marginal likelihood is just what is the chances of the evidence being true. Okay, so I hope this is abundantly clear. This was an explanation on Bayes' theorem.